If you saw my previous video, you'll remember that it was about a mathematical concept called the Collatz Conjecture. And I was looking at some of the programming around that, particularly in C++. And I decided this week I'm going to continue on from that because one of the things I mentioned last week is what I'd done hadn't been particularly efficient in terms of implementing this sequence that involves the Collatz conjecture. And so just as a reminder of that, let's have a look at what we had. Because if I run up the C# program I had last week, we got results looking like this. And here we've just got a couple of examples of the sequence. But the rule of this sequence is we start with a number, so let's start with 6 in this case. And then if that number is even, we simply halve it. So 6 halves to 3. But then if the number is odd, we calculate the next number as 3x plus 1. So that's why it's sometimes called the 3x plus 1 sequence. So with the case of 3, that gives us 10. 10 is even, so we halve it. 5 is an odd number, so 3x plus 1 is 16. 16 halves to 8, halves to 4, halves to 2, halves to 1. And at that point, we terminate the sequence. We've got another example of that for 10. And there immediately we can see the problem that we hit, that the 6 sequence eventually reaches the 10 sequence, and so there is some duplication there. And the program I wrote in the first place simply calculated each sequence without storing previous results, and therefore was somewhat inefficient. So this week I'm going to do something a little bit different in that we're not going to be looking at any specific language feature or programming concept. We're just going to be looking at how to implement this Collatz sequence in a slightly better way. And from that, we'll actually see a number of useful concepts in terms of performance that could be applied in any sort of application. By the end of it, we're going to have a graphical program that will actually show as charts a lot of the information we get from these Collatz sequences. So if we just jump ahead to that and have a look at this first one, this is actually showing us for along the x-axis seed numbers going from 1 through to 1,000,000, and then on the y-axis we're showing the count of the number in the sequence. So in the earlier examples we saw that the 6 sequence had 9 steps in it, the 10 sequence had 7 steps, and we can see all of those for up to 1,000,000. And what we can also see is there is clearly a pattern there. These are not completely random. They are showing some kind of structure. The other thing we can plot, if we just change that, is as well as the length of the sequence, we can plot the peak value in the sequence. So again, if we look at those two short sequences, we can see that both of them actually peaked at 16, but they do undulate up and down, and they will all have a peak value. And once again, we can see there's a clear pattern in there, even if we can't make out exactly what it is. And because of those patterns, we might be very suspicious that the Collatz conjecture must be true that says all of these will terminate. But you've got to be very careful about that sort of thing in mathematics. A couple of other videos I'll link for you related to maths show a couple of situations where a sequence seems to follow a completely predictable rule and then suddenly behaves differently, and that's why we can't make assumptions. One of those has a mathematical formula that you input a number, get out a result, giving you a sequence, and that sequence goes 1, 1, 1, 1 all the way along. The millionth number is 1, the trillionth number is 1, the 100 trillionth number is 1, but when you come to a position of a number with 52 digits in it, suddenly the result isn't 1. And it was assumed it always would be, but it wasn't proven, and with a bit of number crunching, rather heavier number crunching than we're going to see today, it was proved that there was an exception. So let's get down and see how we can start doing this sort of thing for our 3x plus 1 sequence. And the problem we were trying to solve, as I mentioned, was the fact that in any sequence you pick, you will always end up converging onto another sequence. And in fact, these are drawn diagrammatically very often looking like this, where we have kind of railway lines that are joining up together as each sequence joins into another one, and eventually all coming down with those last few steps of 16, 8, 4, 2, 1, as we've seen in the examples here. And in fact, if we think of it as a railway line, then we've got that main line going down the centre of powers of 2, which is always going to be the quickest route back down to the beginning of what we're doing. And where the different branch lines join in there, we're not sure, but if the Collatz conjecture is correct, they will eventually all get on that line and all get down to 1. So I was thinking about how can we, in software terms, do that in the minimum amount of memory. Because in any of these sorts of problems where you're crunching big numbers, you've really got 3 resources you need to worry about. You need to worry about your processor power, you need to worry about the size of the numbers you're dealing with, and you need to worry about the overall memory usage. Now, when it comes to CPU power, it's not something I'm going to hugely worry about, because these sorts of jobs are the sort of thing that you leave running overnight or over the weekend or for a long, long time. So if they're going a little bit slowly, although that's disappointing, it's not the end of the world. The other two problems, though, can actually make the difference between your program working or not. The size of the numbers. So in programming languages, we have 32-bit integers, 64-bit integers, maybe even 128-bit integers. But when it comes to the sort of numbers we're talking about here, although we will get somewhere with those, eventually we'll hit a limit. And the solution to that in C# and other languages as well, there is a class called big integer, which rather than being limited to something like 128 bits, is completely unlimited, though obviously that will be at the cost of both performance and overall memory usage. With my experimentation with this, I've found that the biggest problem has been the overall memory usage. I've got 16 gig on my machine, and in the program we'll eventually put together here, I can process numbers up to about 50 million when I'm doing the calculation of the Collatz sequences, but beyond that I really start to grind to a halt. And the solution beyond that is obviously you're going to have to start storing information in a database or something like that. I've not gone that far, but that's something you might want to have a play with for yourself. But the fundamental structure that I've come up with to try and do this in the minimum amount of memory usage is something like this. If we consider any particular number, so let's start with our seed of 6, then we know that the next number in the sequence is 3. And then if we look at the number 3, we know the next number in the sequence is 10, and 10 is 5, and so forth. And so any number you have, although the preceding number might be different, the subsequent number is always going to be the same. So 6 is always going to be followed by 3. 3 is always going to be followed by 10. So the way I thought about doing this, what if we have just an array where if you index into it on 6, the number being stored is 3. So 6 takes us to 3. We can then look up the index 3. That will take us to 10. We can then look up the index 10. That will take us to 5, and so on and so forth. And so we can have every Collatz sequence there is entirely stored in a single linear array. And that will avoid duplication, and so that should be quite efficient. So that's basically the sort of thing we're going to set up. There are a couple of issues with that. One is it's still not going to be hugely fast. So if we want to go from 6 to 3 by doing a calculation, that obviously takes a certain amount of time. Not very much. We've just got to ascertain that 6 is even and then divide it by 2. But equally, if we do that in the array, going to position number 6 in the array and using it to look at position number 3, is not going to be that much quicker. It's going to be a bit quicker, but not hugely so. But remember, when we're looking at those graphs, we're not really interested in the details of every sequence. We are simply interested in the count of a sequence and also in the peak value that it goes to. So if on our entry for 6, as well as storing the fact that the next entry is 3, we stored the fact that the count for 6 is 9 and that the peak value for 6 is 16, then that would be all the information we need. And when we're drawing these graphs or doing summary information, then we wouldn't need to actually go through the entire sequence. We could just read off that information. And I think that is a pretty efficient way of doing it. But I'm by no means an expert on this, so any other ideas, anybody want to correct me, please feel free to do that, because this is really just me playing around. So let's have a look at how we're going to code that. And what I've got is actually a couple of end programs. I've got my Collatz graph, which is a WPF program that we'll be looking at in a bit to actually do the graphics. But to start with, we've just got this console application that I've called Collatz Cached. And if we look in there, I've already written the code that's going to make use of this thing, even though you can see it doesn't compile because I haven't written it all yet. So basically what we're going to be doing here, though, is we are going to be looping through from 1 to an upper value that the user can type in. So that could be just the first 1,000 or the first 10 million or whatever. And then with this get entry, we're going to get back for that particular seed, we're going to get back what I've called a sequence item. And the sequence item tells us the count, so the number of elements in the sequence for that seed, and also the peak, the highest value that it goes to. And then we're doing some processing on that, and we're going to print out the longest sequence, the highest peak, and some other bits of information as well. So let's see how we're going to put that together. The first thing I think we need to do is put in this sequence item. And in fact, I've already started that off. So there we've got our sequence item. And what I'm going to put in there is we will have a unsigned long that is going to store the current value. We're going to have an unsigned int that is going to store the count. That I'm storing as an unsigned int rather than unsigned long because the count numbers do not get anything like as big as the actual values of the numbers in the sequence. So we'll save a bit of memory by keeping that a bit smaller. I'm going to put in the peak, so the highest number in the sequence. And then I'm also going to put in what probably seems like the most important thing, the next number in the sequence. But for that, I'm not actually going to store it. I'm going to calculate it on the fly. Now, this is a trade-off, really. If we store it, then obviously it's taking up more memory, whereas if we calculate it on the fly, then it's going to take a little bit more processing power. But as I mentioned, I'm finding with this that the limitation is the memory, not the processing power. So although really you've got to experiment to find the optimal level of doing this, I find that it's best to do this calculation on the fly. So what we've got on there is just, if it's even, then we divide by 2. If it's odd, then we're going to have 3x plus 1. So that's what we've got there. And then I'm going to put in a couple of constructors here. And we'll see why I'm doing this when it all comes together. But I'm going to have a constructor that takes that current value. And so just says current equals current. You'll notice it's giving me an error there because if you write your own constructor in a struct, which this is, then you've got to initialize everything. There's an easy way to do that. I can just call the default constructor and that will set the count and the peak to 0. So that's the sequence item, and we should now see in our program it's a little bit happier with most of those things. So now we've got to get this actual calculator working. So you can see that I've got this Collatz calculator. So let's put some code into that. Now remember the idea that we're going to put together here is we wanted to store our Collatz sequence as an array where the index of the array represents one number and then the value of that represents the next number in the sequence. So 6 gives us 3. The problem I'm going to hit with that, however, is it will turn out to be quite a sparse array. Because as you go up the numbers, if you look at, for example, the sequence for 10, the sequence for 10 includes a value for 16, but has nothing for 11, 12, 13, 14, and 15. So if we actually used an array here, it would be what is known as a sparse array, an array which has lots of gaps in it, which are still using up memory. So when you want to implement a sparse array, normally the better way to do that is as a dictionary. So we're actually going to have a dictionary that keys on the first value, 6 for example, and then the value is 3. And although it'll be a little bit slower because dictionary lookup isn't quite as fast as array lookup, it will be much more efficient in terms of memory. And in fact, we'll see when we look at the results of this, it is hugely more efficient. There are a lot of gaps if you do this as an array. But then one other thing we've got to worry about, you'll notice if we look back at the program, again for performance reasons, I'm doing these calculations in parallel. So I've got this parallel for, comes from the task parallel library, which is going to split this work over as many cores as I've got on my processor. So we don't just hog the one core, we use all the resources we've got. But because each one of these different ones is going to be putting data into this dictionary, we have to have that as a thread-safe collection. And everything in .NET, everything in system.collections.generic is not actually thread safe. But there is also a namespace called system.collections.concurrent, which gives us collections that are guaranteed to be thread safe. And so the one we're going to use is actually a thing called a concurrent dictionary. Most of them just put the word concurrent on the front of the thing they're dealing with. So if we go to our Collatz calculator, and the first thing I'm then going to put in there is our private read-only concurrent dictionary, and it's going to have, as we said, the key is going to be a ulong, so that's the particular number we're dealing with, And actually, because we wanted to store not only the next number, we wanted all that information, this is where our sequence item is going to go. So we'll be able to look up any sequence item based on the seed, and we'll just call that underscore sequence equals new and all of that. And then we're going to have a method, as we saw from our program, that's going to be called getEntry, and it's going to return one of these sequences. So it's public sequence item getEntry, taking the seed for our sequence, and then the rules are pretty much the same as we had before. We're going to say if seed is less than or equal to 1, so this is our termination, we're just going to return a new sequence item, and that's going to take in the constructor the seed, and then we'll say peak equals 1, and we'll say count equals 1, because both of those are true, simple for the termination. Then we'll say else, and this is where we need to start being a bit careful because of the multi-threading issue. But that concurrent dictionary gives us lots of very helpful methods. So what I'm going to say is var entry equals sequence dot and then get or add. Now, if you were doing this with a normal dictionary, you would probably test to see whether the dictionary contained the element you want. If it did, you'd use the existing one. If it didn't, you'd create a new one. The problem with that is it's not atomic. If you were doing that in a multi-threaded way, then you could test, discover that an item didn't exist, and then a fraction of a second later, that item could exist. So the concurrent dictionary gives us lots and lots of methods that do these common operations atomically and won't be affected by threading issues. So we want to do the get or add, and then what we do is we say we want to look if there is an entry at the value seed. If there is an entry, just give it us back. If not, then create a new entry using this lambda, where we're going to create a new sequence item initialized for seed. And if we do create the new item, that is what will be given back. Then what we're going to do is we're going to say if entry.count equals 0. Because if it equals 0, we know this isn't one that was in the collection already. This is one that's been created for us. So if the entry count is 0, then we are going to have to determine the count. Again, if we just take a look at the sequence for a simple example like 6, how do we determine what the count for 6 is? Well, the count for 6 is guaranteed to be 1 greater than the count for 3, which is guaranteed to be 1 greater than the count for 10, because that's the way the sequence goes. So all we need to do is get hold of the next entry. So if we say var next entry equals get entry for this entry dot next, so remember we'd written that next to do the calculation for us, then that's going to work recursively. But if this is 6, it will give us the entry for 3. 3 will then act recursively and get the entry for 10. Or those things may already have been calculated when we're coming down other sequences. So now we've got the next entry. The next thing we've got to do is create a new version of this current entry. Because the sequence item is a struct, we can't just modify the values. So we're going to create a new entry. So we'll say var new entry equals new sequence item. And then what I'm actually going to do is add an additional constructor to the sequence item that takes all 3 values. So if I just take that and then also on there have uint count and ulong peak, and then just set those up. And then back here, I can do that. I can say, so this sequence item is a copy of the original one. So entry dot current, and then we're going to pass in the count and the peak values based on what we got from that next entry. So we know simply enough that the count must be 1 greater than it was for the next entry. So next entry dot count plus 1. And then we know that the peak value must either be the peak value for the next entry or the current value if the current value is greater. So there we're going to do a math.max of the current value, which is entry.current, also the same as seed there actually, and then the value that we get from the next entry, so next entry dot peak. So whichever of those is greater is the new peak value for this particular sequence. And then having changed that entry, we've got to go back to our concurrent dictionary, underscore sequence, and then in this case we do a try update. So again, it's got to be atomic, so this does it correctly. And we're trying to update the seed value once again, just like we did the get or add. The value we're trying to put in there is the new entry. But then this try update has a third parameter, which is a guard condition, where we pass it what we think the existing value of the thing we're trying to update is, which should be just this entry. The point being, if between us reading it and us trying to write it back, somebody else has changed it, then we don't want to be overriding it. So that's our try update. So we've got a couple of features of this concurrent dictionary, the get or add and the try update. And then finally, we're just going to return our new entry. And we've still got an else to do, because if the count wasn't 0, then that means this get or add had returned an existing value. And so there we can just say return entry. And again, if we go back to our program, that should be even happier now. But still a few more things we've got to do, because in our summary information, we've done a couple of things. We've got this allocation count. So this was just to demonstrate how sparse the collection is. Remember, I was talking about sparse arrays. So what I can do here for this allocation count is put down here another property. So simply public int allocation count is going to just be the number of elements actually in the sequence. And then another one we had there in the program was the peak value. So that is going to be the highest value we have in the sequence. So again, let's do a public ulong peak value. And that is going to be, again, on the sequence, the maximum of the key values. So that's going to be for a key value pair, but we want to look at the key on that because the key is the seed and we're trying to find the highest seed value. So kv dot key. So that's going to give us the maximum value in all of the processing that our Collatz calculator's done. Then back in program, just one last thing that we're going to look at. So when we've determined which is the one with the longest sequence and the one with the highest peak, we want to actually display just those two sequences. So what we've got there is this sequence, and I'm going to have to add that in. That should be pretty simple because the calculations have already been done. So we're now going to put in here a public IEnumerable of sequence item, and that's going to be sequence, and it's going to take a seed. And then the first thing I'm going to do is just actually call getEntry for that seed, just to make sure that the calculation has been done for that seed. If it has been done, it should come back pretty quickly because it will just return the cached value. But we need to do that to make sure it's done. Then this is going to be very similar to the code we saw last week, actually. So we begin our count as 1, and then we do the very first yield return of the first item. So that's going to be a new sequence item for the seed. And then because it's just the first in the sequence, we're going to say count equals 1. Not actually going to use the max in this circumstance. And then we just do while seed is greater than 1, so terminating when we hit 1, we can say var item equals underscore sequence lookup seed. So that's the really neat bit of using this dictionary, that we just look up the seed to find the next item. So I say seed equals item dot next. So that's what we'll look at next time. And then I do my last yield return of another new sequence item. Again, this time for the new seed and for an incremented value of count. So that will just keep counting on as we go along. And now when we go and look at our program, I think everything should be happy. So if we run that up, and I'm going to put in a value of 10. So it's going to calculate all the sequences from 1 through to 10. And what it's going to discover is that the longest sequence is actually 9 with 20 elements and a highest value of 52. And so we can see that's what we've got there. So there's the 20 elements, there's the peak marked. And then in this case, the highest peak actually happens to be 52. And so there's obviously multiple sequences, clearly enough, that have that value 52 in. But what I've done here is shown the shortest sequence that has the peak value. So that's actually 7, where we can see it going along there. And then also we've just got the most common peaks. So as well as 52 is not actually the most common, 16 is the most common in this case, just lists the top 3 of them. And here we've got this thing I was talking about to show how sparse it is. We've said there are 21 numbers calculated, so 21 entries in our dictionary, but with a peak value of 52. So if we'd done this in an array, then already we would have had 52 slots allocated, but 31 of them wasted because we wouldn't be using them. And that number gets much bigger, as we'll see later on. Let's do this for some bigger numbers. If I put in 1,000 there, then we can see that the longest sequence is 871 with 179 elements, but the peak really shoots up, and we can see we get to the peak there and start coming down. The one with the highest peak, however, has fewer elements but goes up even higher to 250,000 something, and again we can see how that works. And in fact, the most common peak in that case was 9,000, and we can see, as I say, just the top 3 of what we've got in there. But once again, looking at the storage, in that case, if we'd done it as an array, it would have needed 250,000 elements. Doing it as a dictionary only requires 2,200. Let's just do one last one of those, a really big one. And in fact, let's, while we're doing that, show the memory usage. So if I do this in debug and let the debug diagnostics show in Visual Studio, so let's do this for a value of 10 million, which will take a little while, so I'll speed up time for this. But while it's doing that, we can look at the CPU and the memory. So if you look at the CPU, you can see, although it's not using 100%, this is a 4-core machine, so it's certainly using more than 25%, which indicates that the parallelization is probably worthwhile. And then we can see also the memory up to 2 gig already, 3 gig, 4 gig. And then we've got the results. So it's using up 4 gig to store those numbers, which probably indicates, I think I mentioned, I've done up to about 40 million on this, which would really just be hitting my maximum memory. But we can see some of those summaries. I mean, the one that's really quite astounding is the peak value. So that's in any one of those sequences up to 10 million. That's basically the highest reached altogether. And that is 60 trillion. So even though we've only calculated 21 million values, the highest of them was 60 trillion. Again, if you imagine trying to store that in an array, it would have been almost entirely empty, and that's why a dictionary is a much better solution. And in fact, we can see in terms of the most common peaks, however, you can see that 6,800,000 and whatever is a very, very common one. And then if we look at the 2 sequences it's printed out, the longest one, under 10 million, was 8 million and something, got 686 elements, and its peak was 159 billion. And if we scroll down, we can see there is where it reached its peak. And then the one with the highest peak, which should come next, a bit shorter, but that was the one that hit that peak of 60 trillion. So absolutely huge numbers involved there. Still, thankfully, within the range of an unassigned long, but we're going to be hitting the limit fairly soon, and you can see why big integer is the sort of thing we might want to use in that case. Okay, and then finally, just very quickly, let me show you this extra program I've written for the graphing. So here we've got this Collatz graph. If we just run it up first, we can take a look at the GUI. So if we do, let's say, 1 through to 100,000 and click on generate, and that's the count, and we can really see a pattern starting to emerge. If I click on peaks, you can see something of a pattern there, but you'll notice this clip Y2. If I were to leave that at 100%, the problem is that because some of the peaks are absolute extremes, you may not be able to see it, but it's just up there, you can see the highest peak, and it's crushing everything down. So one way to get around that, I could have done it on a logarithmic scale, but I've just done this. So if we only show, in this case, the bottom 0.1%, then we see a bit more of a pattern. Let's do one last big one. Let's go up to 5 million. And let's look at the counts first. And you can really see that there's a pattern happening in there. If we switch to peaks, already we can see a pattern. I think even 0.1% is a little bit large there. So let's focus in on maybe, let's do the bottom 10th of what we're seeing there. So 0.01%. And we can really see two distinct patterns. We've got the diagonal lines that are quite obvious, but also these very, very common horizontal lines where there are particular peaks that are happening again and again and again. I'm not going to do any mathematical analysis of that, but it's quite interesting. Clearly there are patterns going on there, but there are people much smarter than myself who know what those sort of things mean and have gone far bigger in terms of numbers. But I hope that was interesting. The things to take out of that in terms of C# programming, I think, are looking at the things like the parallel for, which allows us to spread the coding across multiple cores, but then the fact that that requires the necessity of having things like the concurrent dictionary. So next time, I think we're going to be back to something rather more mundane, but hope you enjoyed that. Do subscribe, and I'll see you soon.